Hello everyone, I welcome you all to this video tutorial series in Basic Electrical Engineering. In this video, we will learn about the Thevenin's theorem. So this Thevenin's theorem is used for simplifying an electrical network. So here we can see a circuit. So in this circuit, what we can see? In this circuit, we have resistances R1, R2 and R3. We have a voltage source V1 and we need to find out the voltage across this point A and point B. Suppose this is the requirement. So the Thevenin's voltage is the open circuit voltage at terminals A and B. So this VAB will be the Thevenin's voltage. And we have a series resistance with this Thevenin voltage. VAB is the Thevenin's voltage and small r is the Thevenin's resistance. Thevenin's resistance small r is the resistance seen at AB. This is the AB terminal, okay, seen at this terminal AB with all voltage sources replaced by short circuit and all current sources replaced by open circuit, okay. So what we have to do, if we have a voltage source like this one, we have to replace this voltage source with a short circuit for finding out the Thevenin resistance. And if there is a current source, then we have to replace it with a open circuit. Okay, open circuit means infinite impedance. So the Thevenin's equivalent circuit will look like this. This is the Thevenin's equivalent circuit. Here we have a Thevenin's voltage VAB. We have a Thevenin's resistance small r here. Okay, and the terminals are A and B. We have to consider the points A and B. This is point A and this is point B. And across these points, we have to find out the Thevenin resistance VAB. Again, we have to find out the Thevenin resistance small r. And the small r is found out considering the voltage sources replaced with short circuit and the current source is replaced by open circuit. So we have to follow this principle for finding out the Thevenin's equivalent circuit. This is suppose the considered network. In this network, we can see that we have a voltage source. The voltage source is this one, E, and the EMF and the voltage value is capital E, and the internal resistance is small r. So we have already seen that for finding out the Thevenin's resistance, we have to replace the voltage source with a short circuit. But in this case, we have a internal resistance. So if we have an internal resistance, then we have to replace the voltage source with the internal resistance. Suppose we need to find out the current flowing through the resistance RL. This is the load resistance RL. Suppose we need to find out the current flowing through this RL resistance. So how we can find out? So we have to use some step-by-step procedure. Okay, we have to proceed as the following steps. So in the first step, what we have to do? In the first step, remove RL from the circuit. So this was the circuit. So we have to remove this RL value. Okay, RL resistance. We have to remove it. Okay, we have removed it. Now this A point and B point, this is open circuited. Okay, and we have a voltage. Suppose VOC across these points. In the first step, we have to remove the load resistance in which we want to find out the current. Okay, now this VOC is the open circuit voltage after removing the RL resistance. Here we had the RL resistance. Now we have removed and we have to find out the voltage across these points A and B, and the remaining part of the circuit remains the same, and this small r is the internal resistance I have written here, and this E is the EMF value or the voltage source value. So all the remaining part of the circuit is remaining the same. Now in step 2, what we have to do, calculate the open circuit voltage VOC. So we have to find out the VOC voltage. Here we can see this is the VOC voltage. After removing the load resistance, we have to find out the voltage across these points A and B. Now here we can see this A point and B point. These 2 points are directly connected, no other element inside this A and C. We can consider the A point same as C because we do not have any resistance in between. Similarly for point B also, we do not have any resistance between B and D. So if we find out the voltage across A, B, this will be equal to VCD. Okay, you can see here, because we do not have any resistance, this and this is nothing but VOC. VAB means VOC. So in this way we have to see. Now, in the second step, we have to find out the VOC voltage. So, how we'll find out? So, first of all, we have to find out the total resistance. This is nothing but the total resistance. So, total resistance, if we open circuit at the points A and B, these three resistances, they are in series connection. Okay. If we remove this, now let me show here. So after removing the load resistance, now we have, this is the circuit. Okay, we have another resistance here. So we can see here, this R value, this R1 value and this R2 value, they all are in series connection. So what will be the total resistance? We have to add them because they are in series. So the equivalent resistance or the total resistance will be this much. R equal to R1 plus R2 plus R. This is the R1 value, this is the R2 value and this is the R value. R value is the internal resistance of this voltage source. Now we have got the total resistance. If we divide the total voltage, that is the E value, with this total resistance, we will get the total current. So the total current value is given by this one. Now we have to find out the VOC. We have to find out the open circuited voltage. These 2 points means the total current I is flowing in this direction, and this I we have to multiply it with R2 because from Ohm's law we have V equal to IR. So we'll use that formula. So VOC, that is the open circuited voltage, equal to I into R2, because the voltage across this point C and D is equal to VOC. VOC is equal to VCD equal to IR2. So here we have multiplied the total current with the resistance R2. This is nothing but the Thevenin. This VOC is nothing but the Thevenin voltage. In the third step, we have to find out the equivalent resistance or the Thevenin resistance. So we have to find out the equivalent resistance as seen from the load, and we have to minimize this circuit from this side to this side. Okay, from left to right. So here we can see these 2 resistances are in series connection. So R1 plus R is in parallel with this resistance R2. The equivalent resistance will be R1 plus R2. Here you can see is parallel with R2. So R1 plus R. So R1 plus R is in parallel with R2. So R1 plus R will be multiplied with R2 divided by R1 plus R2 plus R. Okay, so this will be the equivalent resistance. This R value is also known as the Thevenin resistance, RTH, or we can say that RTH can be denoted with RI or R naught. R naught means it is the open circuited resistance of the network. Okay, in the fourth step we have to again connect the removed RL. In the first step we have removed the load resistance. Here you can see, in the first step we have removed the load resistance. Now in the fourth step we have to again connect the RL to the circuit as shown below. So after finding out this VTH value and RTH value, they will be connected in series connection, and these values will be connected to the load resistance in series connection. Now this load resistance is connected to this Thevenin equivalent source. This Thevenin equivalent source is nothing but a voltage in series with the equivalent resistance of the circuit, as this resistance is seen from the load side. Okay, and this VTH value is found out using the total resistance and total current, okay, in the network. After connecting this load resistance, we can find out the value of this I. Okay, this is the total current because this is a series connection. Okay, so in series connection all the current values will be the same. Okay, the voltage drops will be different but the current values will be same. Okay, now we will find out the current flowing through the load resistance RL. This I is equal to VTH divided by RTH plus RL, because we have only one voltage source and we have 2 resistances connected in series. Current flowing through this load resistance is capital I, and this capital I value is this one, VTH divided by RTH plus RL. So this is the formula for finding out the load current. Now let us define the Thevenin's theorem. So Thevenin's theorem states that for any linear electrical network containing voltage source, current source and resistance. This voltage source should be a DC voltage source. Okay, and if a network contains a voltage source, current source, and resistance, this can be anything, anyone also. If any one of them also exists, no problem. So in any electrical linear network containing voltage source or current source and resistances can be replaced with a equivalent resistance, equivalent combination of voltage, that is also called as the Thevenin voltage, and in series resistance. So we have replaced, or we have simplified the network to obtain this. The RTH is the Thavenin resistance and VTH is the Thavenin voltage. Okay, and we have connected the load resistance in series with them. So according to Thavenin's theorem, we can replace all the resistance and voltage sources with an equivalent voltage source known as the Thavenin voltage and an equivalent resistance, that is the Thavenin resistance. So this Thavenin's theorem helps us to minimize an electrical network. This much for today. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Thank you.